Hello, today we're going to talk about the absolute value function. We're going to talk about absolute value equations and inequalities. The absolute value function can be represented numerically in a table where the input -3, output will be 3, input of -2, output will be 2, and similarly the input of positive values will output positive values. And this has a V-shaped graph when we graph it. And with this V-shaped graph, our piece on the left will be y equals x. No, it isn't. Y equals a -x for x values that are less than 0. And on the right, we have y equals x, and this is for x values greater than or equal to 0. So each piece of it has its own representation. We're going to use this again in a minute. Notice that if the input is -3, x value less than 0, a -3 gives an output of 3. What you put in is what you get out on the right-hand side. Input 5, you get 5. Input 8, you get 8 out. In general, the domain is all real numbers. We can put anything into an absolute value equation, standard linear absolute value equation. The range is only non-negative values. We do not call these positive because 0 is included, so they're non-negative. The graph is increasing on the right, so when x values are greater than 0, and it's decreasing for all x values that are less than 0. Now, we're used to seeing the absolute value function written as f of x equals absolute value of x with these straight lines. But there are two other representations of the function as well. One we could write based on the graph that we just saw above. And we take those two pieces, y equals x for x greater than or equal to 0, and y equals -x for x less than or equal to 0, and we call this a piecewise defined function. We'll talk more about this in a later lecture, but a piecewise defined function is defined in pieces. It's a function, so it has all the properties of a function, and it's defined in pieces. The third representation, other than just the symbol that we're used to, the piecewise defined function that is more mathematically acceptable, we also have a radical interpretation. When we take the square root, when x is any real number, and we take the square root of x squared, this is the absolute value of x as well. So this one is not quite as well recognized, and I don't think we emphasize it quite enough in classes as well, but that's a good one to keep in mind. All right, so now that we know what we're working with, all right, it's linear pieces of a function. We know what happens, how it's described. Let's work with it a little bit, and let's start with a property. Let k be a positive number. Okay, so k has to be positive. That means it can't be 0 either. Right? Positive numbers are strictly positive. Then the absolute value of ax plus b equal to k is equivalent to ax plus b equals plus or minus k. All right, so only if k is a positive number. So what do I do if the absolute value is equal to 0? Well, the only way that something can be equal to 0 is if that something itself is equal to 0. We can add 16x to both sides, divide by 16, and get 7/16 for an answer. We don't have to work any harder than that when it's equal to 0. Again, k must be a positive number because the absolute value has an output or range that is only positive numbers. So when we see an example like number 2, the absolute value is equal to a negative, this is impossible. The range is non-negative. So my answer will be no solution. Right? No solution if the absolute value is equal to a negative. But don't just memorize that property. Think about it, what it really means. The absolute value itself cannot be negative, but this equation has some more action going on. Just because you see the -1 over here on the right doesn't mean that automatically no solution. Let's isolate the absolute value part. So I'm going to put that over here. Isolate the absolute value. So I'm going to add 5 to both sides. When I add 5 to -1, I will get 4. Don't forget that little absolute value side. And now we can use the property. we always have to isolate first before we could use the property. And the property says that the absolute value of 1.2x minus 1.7 equals plus or minus 4. And that's exactly what the property said. So we do 1.2x minus 1.7 equals 4. And we'll do another problem that is 1.2x minus 1.7 equals negative 4. So we want to solve each of these individually. We'll have two answers here. When I add 1.7 to both sides, add 1.7, I'll get 1.2x equals 5.7. When we divide both sides by 1.2, we'll get x equals, 57 divided by 12, essentially. What would that be? We should probably take out a calculator. Calculator. I should be able to do this in my head. I know I could simplify this. But you have no idea how much the brain frazzles when you're doing a recording. So we'll get x equals 4.75. Similarly, when we add 1.7 to both sides, 1.2x equals a negative. So 4 minus 2 would be a negative 2, but we're not subtracting the full 2. This is a negative 2.3. Divide both sides by 1.2, and we'll end up with x equals a negative, use our little handy calculator here, negative 2.3 divided by 1.2. And we'll have, ooh, that's ugly. I'm going to use this math button and simplify that into a fraction. And it looks like that can't be simplified at all, so we'll just use our fraction, negative 23rd twelfths. Now, we don't usually write a fraction with decimals in the numerator or denominator. This is considered to be a complex fraction because decimals are fractions. So we'll have a fraction in the numerator, fraction in the denominator. That's bad form. And in math, we always want to simplify the decimals out of both numerator and denominator. So here's our answers. Both of them are true. And you can always substitute back in for x and make sure the original is accurate, is true. All right, now a double absolute value equation, it seems like it might be double the work, right? But the property says once you have an absolute value isolated, we will have 2x minus 9 equals plus or minus the whole right-hand side. So we will have 2x minus 9 equals 8 minus 3x. And we will have 2x minus 9 equals negative 8 minus 3x. Let's do this one first. We have to distribute this negative sign. We'll have 2x minus 9 equals negative 8 plus 3x. Let's take our x's over here. We'll have 1x, which we frequently write as just x. Let's add 8 to both sides. Negative 9 plus 8 is a negative 1. So we'll get x equals negative 1. On the first equation, where we're using the positive value, we can just, let's do this correctly. Nothing to distribute to start. So let's add 3x to both sides. We'll get 5x, add 9 to both sides. And we'll get 5x equals 17 to find x equals 17 fifths. Our two answers that we can check and make sure they're going to work out. All right, so don't feel like you have double the work. You just have to remember to distribute the negative sign to everything on the right-hand side. Fantastic. Now let's look at a word problem. The maximum and minimum lawful speeds s on an interstate highway satisfy this absolute value equation. If I want to find the maximum and minimum speed limits, I just want to find s. All right, that's a fancy way of saying solve for s. So let's do that. We know s minus 57.5 will equal plus or minus 17.5. So that's s minus 57.5 equals a positive 17.5. I'm going to add 57.5 to both sides. We'll get S equals 5 and 5 makes 0. That's good. We don't have any decimal speed limits here in the States. A 14 plus 1 makes a 15. 5, 6, and 75 is the maximum speed limit. Similarly, we have S minus 57.5 equals negative 17.5. So easy to forget those negatives. I had to cram it in there. Plus 57.5 on both sides. And we end up with S equals 57.5 minus 17.5. This is 40 miles per hour minimum. That's it for absolute value equations. I'm going to call this part 1 of the lecture. Part 2 will be absolute value inequalities.